Okay. Good evening, everyone. My name is Vishwanath. I'm a Python developer at UMM Digital, and apart from that, I work on an open source project which is aimed at abstracting human memory onto a computing system. So my talk is going to be about that. It contains a lot of math stuff, so I'm sorry it's a tad bit too much math. Okay. So my topic for today is going to be like AI and human memory, and it's basically a primer between what is an AGI system and how you can use it to power storage systems. So it's going to be pretty straightforward talk. What the introduction, what are patterns, what is a hippocampus, how we came about with the entire simulator idea, and how we are correlating the simulator between brain and the computing system, how auto-associative networks work, the current algorithm, and how the results of it basically. So everyone, how many of you here have heard about AI, like artificial intelligence of some form, neural networks, machine learning, yada yada yada? Okay, great. So almost everyone. How many of you have heard about AGI systems, artificial general intelligence? Okay, great. So when the AI researchers started out, they wanted to build systems which could think like human. But at one point, they couldn't optimize it any further, and that's what that period is called as an AI winter and stuff. So why they wanted to do that was, a human brain in general can store around 2.5 petabytes of data. And today we mostly deal with TBs of data at max, and the TBs of data is stored in this bigger chip, but 2.5 petabytes of data is stored in like a very minimal space system. So our brain must be doing something right, so that our entire storage systems can be shrinked into a very small piece of hardware. So that is where it started, and it led to this. So where we deal with only patterns, like our entire life is built on patterns. For example, every morning we have a routine, like we get up, we do our morning tasks, then we go to school or college, then we come back, and then we do certain tasks. So everything is ingrained as a pattern, and these pattern gets strengthened depending on how frequently you do it. For example, if you start writing daily, you write faster. If you start typing daily, you start typing faster. So a person called David Marr came up with the entire theory that the hippocampus was responsible for storing information, and it was one of the first theories which aimed at solving general intelligence. So his entire point was that, being one of the earliest regions to develop, it can be said that hippocampus is the starting point of the evolutionary route. So you think starting from your hippocampus, and that is pretty much why we started focusing on that region. So hippocampus is a very complex structure involving your dentate gyrus, your CA1, CA3, your subiculum, and goes back into your EC3. Forget this image, this is all that is required for us to develop the system. So EC2 is where your normal input comes. For example, every day you see an object, may it be a dot, or may it be a line, may it be like an ice cream, or whatever you guys are excited by. The entire processing happens in your rods and cones of your eye, and the input reaches your EC2. So what happens is, EC2 sends the data into dentate gyrus, and it also sends it to your CA3. So when it comes, you're like, so okay. So your dentate gyrus is the place where your auto association of your memory takes place. You will see it in the coming slide. But like what happens in hippocampus is, your dentate gyrus in your hippocampus is responsible for converting your short-term memory into a long-term memory, which is then stored into your neocortex, completely different region again. But in your dentate gyrus is where your pattern starts, and your pattern starts to strengthen over a period of time. So what happened was that we found that in the hippocampus region, pattern completion and separation are some of the most important tasks which take place. So we again isolated pattern completion as when pattern is retrieved, and pattern separation is something which happens during storage of the same thing. So we started building a pattern storage engine, and then we moved on to build a pattern completion engine. So what we found was that the dentate granules, or the firing rate of the dentate granules, decides whether a new memory is formed or not. Though the new memory is formed or not is detected by the CA1, the initial patterns is created in your dentate gyrus region. And so we basically determine the novelty in a different region and assign a new pattern in your dentate gyrus. So you can ask me, like, how do you correlate between the two? So any neuronal activity is depending upon the electrical impulse which it basically gives out. So whenever there is a strong electrical impulse, it can be treated as a 1, and whenever there is a weak inhibitory impulse, it is treated as a 0. So you just have to translate that into a computing system which primarily deals with 1s and 0s, and say whenever your electrical impulse is above a certain threshold, store that memory bit as 1, and whenever it is below the threshold, store that bit as 0. So it is very easy to model your data storage systems based on brain, but you will see further as to why it is not as easy as it sounds. So when I give these two statements, how many of you can fill it? Like, yeah, go on. Okay. So did I give you, apart from these two lines, did I ever give you any context regarding from where I am asking? Okay, so to be or not to be, that is not the question, could have also been the statement. But our brain automatically associates the starting with that is the question, and that is where your pattern completion takes place. And your brain, or more specifically your dentate gyrus region, functions as an auto-associative network, and make sure that the pattern which you are getting is completed in some form and strengthened over a period of time. Now, so for modeling your auto-associative networks, you use something called Hopfield networks, where say every connection in your Hopfield network, which is basically the 4 dots that you can see and all the lines going around it, can be described using a very simple connectivity algorithm called which basically says it is +1 if it's above a certain threshold and -1 if it's below a certain threshold. So did we ever realize like it's going to be as simple as a +1 -1? But it apparently is, and so that is when we came to this big algorithm that you see. So what initially happens is that you get an input vector x, which passes through the activation function which you saw earlier, which determines if this is a new connection or an old connection, based on +1 -1 and the earlier patterns which we had stored. Now what happens is it undergoes something called a mutual inhibition, which says that hey, I am activated, I am not. So it is possibly going to be this memory. For example, if I show you the image of a kitten, okay, and I take you into a real life and your cats are moving around along with dogs, will you be able to distinguish which is a cat and which is a dog based on one image of a cat? Yeah, but can you try to distinguish even with very minute accuracy, like say even a 10% accuracy? Yeah, so studies have found that even a small stimulus can lead to a 50% accuracy in recognizing an image similar to that, and once you start recognizing new images, the connection develops as good as 100%. something that your neural network still can't achieve. So what happens here is that whenever a new pattern comes in, it mutually inhibits each other's. Let's say if there let's say these are the four neurons which are present in your brain. Let's name them 1, 2, 3 and 4, and some stimulus comes in which activates 1, 2 and 3, so what a dentate gyrus does is it says if 1, 2 and 3 is activated, it is X, and it sends it to neocortex. So whenever any activity fires 1, 2 and 3, you associate it with X automatically. So that is why when I told I saw, automatically you guys said I conquered, because your brain is subconsciously wired to the fact that I conquered is what has to come next regardless of the context. So now what happens here is you need a learning algorithm even here, but it is more like an associative learning algorithm where there is nothing called back propagation at all. So your learning algorithm is by beating down each other and saying, hey, these are the patterns which are getting activated, and that is why the memory is corresponding to X or Y or Z or whatever. Okay, now at the end we have to normalize the vector, because so you have a very finite number of neurons which exist in your brain. So whenever there is a very finite number of neurons, you can't have infinite vector sequences. So you boil it down into a finite vector sequence by the method of normalization, where you just so we use a very simple normalization method where we just divided the entire thing by the sum of that particular row. But there are more complex normalization methods which is computationally intensive, but our brain seems to do it pretty easily. Now this was about the pattern storage as such. Now how do you recall a certain pattern? Like, say I've stored my pattern in, and how do I actually do it? And that is where your inhibition comes into play. So what happens here is your pattern, as said earlier, comes in from your EC2 region into your dentate gyrus, which then undergoes a mutual inhibition to check with each other if they are activated or not. So let's say if U3 exists and U3 are getting a certain data. So what happens is U3 asks each other if you got activated. If you did get activated, then it all normalizes to a certain sum at the end, and that sum is corresponding to a particular memory block. Now the results which we achieved with this was that we were able to increase the number of patterns stored per neuron from by almost 30 to 40%. So what happens is when you have a 1000 neuron sequence and 200 patterns are incoming, each pattern of the length 10 power 16, what happens now? You can clearly see that the difference in pattern storage is extremely high. It's almost double. So going forward, when we tested our simulator on a neuron sequence of 15,000, we were able to see a significant jump of up to around 252%, which was with the dentate gyrus. Now more than storage, what most people are worried about is the retrieval. Like, if I store, how do I retrieve? Now what happens here right now is that our model still isn't as competitive as what we would like, but the percentage of error in each output of retrieval is extremely less. Like, it's much lesser than what you do without using your dentate gyrus. So that's pretty much an overview of the system. Do I have time? Yeah. So I'll just take you through the code base. Okay, so this is what we did for our dentate gyrus. Like, so So initially it comes into this function where it has like an output layer and the output functions and stuff. So we see if the computation has to take place. So for each row, that is each pattern, we check if the computation has to take place, and then we calculate the y parameters for the same. So what happens when we calculate the y parameters is that it goes into that very complex algorithm which I just showed, and what it does is it basically normalizes each input and then sees if this input is corresponding to any existing pattern, and then keeps returning those values, which is the sum which I mentioned. And if the values is the same, then it gets added onto a result list, which automatically becomes the output layer for your dentate gyrus to be pushed onto your neocortex. Now when retrieving, we use something called your Oja's rule, which is your associative learning rule kind of thing, which again follows a very similar process, but this time it works with something called the dilution component. So what happens in a dilution component is that if you have 100 parameters, you don't need 100, you probably need 50 or 80 or something. So it calculates your dilution component, and then it calculates the maximum dilution required for each pattern. Based on that, it first activates a node and then extracts the pattern. Yeah. So what happens is whenever you have your say first thing, obviously it gets sorted because most of your activation nodes become 0, since you are like you process data and then you decide, okay, these nodes are not required to be activated. So those are pushed towards the end of the stack using by sorting it, and then we take the top n elements which is required based on a competitive learning strategy. So the competitive learning is like, say if you're competing with 10 people, we need to decide the top 10 winners. Top 5 winners. So for that we have multiple criteria to do the same. I am sorry I don't have time to dive into the criteria, but you can contact me later if you would like. And what happens is that then we take each of these activated indices and map them onto 1 or 0 depending upon whether they are activated or not activated. So once that is done, we get out a result which is more like an activation map of sorts, and the activation map basically tells you whether the pattern that you actually stored was retrieved or you basically got some junk value. So we generate all the input patterns that we are storing based on some randomly generating binary numbers and storing it on the files. We feel that is the most easiest way to do it, but we tested our system on NS dataset and we were able to achieve like this is not your accuracy in terms of in terms of detecting whether the number is 1 or 9, but whenever you store a certain pattern as say 9 and you want to retrieve all the images of the number 9, it basically does that. So, and the retrieval component is much faster than your traditional storage systems. So it's like faster than your traditional storage systems, but not as fast as we would like again. So we're still running tests and we're trying to optimize it further to see if it works for more say regressive data, like your Twitter data streams or Facebook data, Facebook feed streams, etc. So future work, one thing that we are working on right now is converting this into a key value storage engine, so that tomorrow whenever I have a certain key, I can get all the values for it based on auto association or things like that. And we are also simultaneously working towards replicating the same work for other regions like CA3, etc. But again, I don't know where that is going, to be honest. Okay, so about me, like I'm a Python developer, Digital. That's my website, my email. This is the project repo. It's completely open source. You guys can take it, do whatever you want with it, and just mail me if you guys find something fruitful.